Hey, today we're happy to have Anson Hook from the University of Maryland, who will tell us about dion bound states.
Yeah, thanks. Thanks for giving me the chance. Very excited to see you guys all again, even if it's just virtually. So yeah, today I'm going to be talking about bound states and work done with one of my students. And so I guess I don't need to tell all of you guys that monopoles are obviously a good idea, right? They make Maxwell's equations more symmetric. The thing I personally like the most about them is that they're a very good explanation of quantization of charge. So if anyone hasn't done this before, it's a really fun exercise that I suggest people do, which is take an electron at rest or a charged QE particle at rest, take a monopole at rest, sources magnetic fields, and calculate the angular momentum stored in the electromagnetic field, right? You take the Poynting vector, E cross B, R cross that, integrate over all space to get the total angular momentum. And what you'll find is that turns out if you properly normalize your electric and magnetic charges, you get an answer that's h bar over 2. Now, one of the first things we learned in quantum mechanics is angular momentum is quantized. And so if angular momentum is always equal to h bar over 2, then if you discover a monopole of some charge, then all electric charges have to be quantized in units of basically 1 over that for some particular normalization. Another way people might have more traditionally seen this is that to make sense of a monopole, or people often will include the Dirac string. However, you require the Dirac string to be unphysical. And quantum mechanically, there is the Harnaud-Bohm effect. Namely, if you take an electron around the Dirac string, you acquire some phase proportional to the flux. And if you require that effect not to be present, then you also get quantization of electric and magnetic charges. So aside from this sort of fun stuff, there are two additional things that I think are pretty interesting about monopoles. The first is that they break symmetries in a way that's basically very dependent on your ultraviolet completion while not being suppressed by the UV scale. This is something typically called the Kalin-Rubakov effect. And the second thing is that due to the Witten effect, monopoles are sort of don't come by themselves. They come with a whole family of states called the dyons. So let's sort of briefly go over these. The first is the Kalin-Rubakov effect. And so to see this, what you can do is you can take an electron, um, let's say a right-handed electron, you throw it at a monopole, and if you look at it and you aim very carefully, you can say this thing, it's right-handed, so it has spin 1/2 to the left. The electromagnetic field has spin 1/2 to the right. Add them together, and you see your total angular momentum is 0. So you're throwing in your electron in an S wave state. The electron. So what happens through most scattering processes? Most of the time you miss, not much happens. This is why whenever you do S matrices and things like that, you factor out a 1. Most of the time, nothing happens. So what happens if nothing happens? Well, I'm coming out the other side. So if the angular momentum from the E and B field is pointing from the monopole to the electron, at least from this classical picture here, it's pointing to the left. I had said nothing else changed, right? The spin is unchanged, the momentum is unchanged. It's also pointing to the left. And you'll notice you now have not conserved angular momentum. And so this effect is basically just saying if you throw in an electron or really any fermion at a monopole, nothing can't happen. Something has to happen. And you don't actually know right off the bat what happens. It can either, so for example, conservation of angular momentum says something has to happen, namely, it has to turn from a left-handed particle to a right-handed particle. You don't know if it changes identity in the process, electron, proton, muon, whatever else. And so this is just saying that when you throw in some S wave state, what comes out must be different than your incoming state. So you must have broken some sort of symmetries, manifested in basically a boundary condition at the core of the monopole. So in this approximation, we're just taking it to be infinitely small. So I'll sort of come back to this a bit later, but for now, this is all we really need to know, namely monopoles come with boundary conditions. These boundary conditions break some symmetry of your problem, whether it be chiral symmetry, baryon number, lepton number, depends on your UV completion. The next thing that I said was I liked about monopoles was the Witten effect. And so monopoles, the Witten effect is the statement that monopoles carry charge theta over 2 pi. And so the easiest way, sort of a very quick classical-ish way to calculate this, is you integrate all of your particles, you go to very long distances, and you take the FF tilde term, which is where theta appears, write it as E dot B, sort of integrate by parts to take the divergence of A0 into the divergence of B, which is a delta function wherever there are monopoles. And so what you see is that a source for magnetic monopoles, right? A monopole is a source for the magnetic field. At the same time, sources in A0, which is a charge theta over 2 pi originating at the monopole. So this is saying if you put in a source for monopoles, you also get a charge theta over 2 pi. Now, this turns out that monopoles have to come with some dyon friends. Why? Because physics is 2 pi symmetric, right? If you take this initial term here, this FF tilde, you shift it by 2 pi, this theory is identical to itself. And what that means is because this electric charge, this theta here, the Witten effect is not periodic. The only way to make it periodic when you shift theta by 2 pi is if you sort of have an exchange symmetry here, right? So there's some hopping here as the monopole turns into a charge 1 object. The charge 1 object turns into charge 2. Charge -1 turns into a monopole. And so this is the only way to make the theory 2 pi symmetric. And since we had added monopoles to the theory, the periodicity of theta forces this tower of dyons to be about. So
That's not what happens in Seiberg-Witten, though.
yeah, so in Seiberg-Witten, I'm going to have to remind myself a little bit more what happens there. I thought this was what happened, but then that the monopole state was massless. So the masses of everything was changing too. So as you change theta, the masses changed. That being said, in Seiberg-Witten, is there a massless? I think there are, well, at least in the n equals 2 supersymmetric case, there are massless fermions. So that theta is unphysical. So you'd have to start adding mass terms, which is breaking it to the n equals 1 version. And I don't remember when you break it to n
I
equals
mean,
1. Sorry.
mass terms don't break supersymmetry, but you could just do it without any flavors. Then
Yeah.
inside the curve of marginal stability, there's just the monopole and dyon states. And so they do things as you change theta, but when you go around by 2 pi, there's just a monodromy and you come back to the same physics in a different description, and then you're free to
Yeah.
change
So the
descriptions
physics is
back.
exactly the same, but what you called the monopole has turned into your dyon. You sort of exchange identities.
Right. So there's no tower.
Uh, yeah, so one thing to note is that these tower dyons do not necessarily need to be like a single particle state. So for example, this two charge 2 dyon could just be a charge 1 dyon plus a W boson or plus a fermions and things like that. So this doesn't have to be a one particle state and comparing it to another one particle state.
If I start with a one particle state and shift theta by 2 pi, don't I have to get a one particle state?
Well, I
Uh,
think you have to get a state, don't you have to get a state with the same energy at least?
you have the state with the same quantum numbers under everything that's non-anomalous,
Right. And
but
energy.
not even the
Energy
same
is one of
period,
those.
right? you don't even need the same energy, because just because you have, say, these two things are equivalent to each other, or one smoothly transitions into the other. So for example, you definitely have, as you vary theta, you change the electric charge, so you change the electromagnetic energy, right?
Right, you
So
can have monodromy, that's right.
yeah, and so in
But
all these cases where there's a monodromy, which is what happens here, you don't actually go back to yourself exactly. You go back to a different state with different energies, same quantum numbers minus anything anomalous.
it has the same mass, right?
Well, no, there's
So
not.
what happens is these dyons have different masses, but as the mass, let's say, but you start off with a charge -1 guy. As theta increases to 0 to 2 pi, its mass changes so that at 2 pi, its mass is exactly the same as that of the monopole, because now it's the new monopole.
I guess they don't have to be stable, for example, though.
Yes, that's right. They don't have to be stable. And
But
in fact,
if you start with a stable particle, you have to, and after 2 pi, you come back to a stable particle.
No.
well, it's more like an unstable particle has turned into a stable particle, right? That's the monodromy of like the identity of states are changing.
The monodromy means they differ by a duality transformation, but the physics is equivalent,
Yes.
right?
But
So
the labeling.
stable is a statement that doesn't change under duality. It's
The
either stable.
spectrum, the whole spectrum has to be invariant, but the states don't have to go back to themselves.
Yeah, that's right.
Well, under monodromy means they go back to themselves up to a duality transformation.
But the duality transformation mixes states. When you do a duality transformation, states get all mixed up, right?
Well, a state with a definite mass that's stable goes to a state with the same mass that is also stable.
After you've renamed all the states, after you've scrambled all the
Yeah.
states. The standard
Well,
picture is just that the whole states, like you have two states and they just exchange places under a 2 pi rotation. That's the simplest example. The spectrum goes to the spectrum, so everything is invariant, but a stable thing can become unstable and vice versa.
Mm-hmm.
And then
So
the
like
duality is that you can do this, you can
that's
flip them. That's the duality. You can take this spectrum and rename it that way.
Renaming things can't change its mass or its stability.
You're, I don't know.
Duality is renaming. Mass is invariant under what name you call it. Stability is invariant under what name you call it.
yeah. I mean, I would say here, since I'm imagining sort of monotonically slowly increasing theta from 0 to 2 pi and asking how are the states when you have theta equals 2 pi related to the states when you have theta equals 0? So in other words, this theory, if you deform it with theta here, is 0 is equivalent to the state of 2 pi because it's periodic. You have the same. But the way you call something in the theta equals 0 theory and the way what you call it in the theta equals pi theory may differ. Because maybe in the theta equals pi theory, you labeled it by back when it was theta equals 0, and then slowly adiabatically changed theta without changing your naming convention. So what you wanted to call your monopole now has electric charge, so you want to undo that. But this is sort of, well, maybe I should just go on since I think this is going to be roughly speaking ancillary to most of the point.
Great.
But yeah, if it comes up again, bring this up again. So what I wanted to do next is just say, when you actually calculate something like the Chuff-Polyakov case, how do these Dyonic states manifest themselves in just some SU2 theory with phi and nothing else? So famously, Chuff-Polyakov monopole, take SU3 with a scalar adjoint, and that's it. And because this theory, when you break it down to a U1, has non-trivial mapping of the ground state to infinity, there are monopole solutions. It is worth mentioning that this theory breaks SU2 down to U1 and there's an extra Z2, which is the center of SU2, that it remains unbroken. And so if you try to track too carefully about things like what is the fundamental magnetic charge and things like that, you're sometimes a factor of 2 off because of this extra unbroken Z2. But that might appear later on. So the solution here is just, you say the scalar vev proportional to R, and the gauge field also epsilon times R. But the important thing to note here is that one, the base Topf-Polyakov solution has A0 equals 0, so no electric charge. I'm taking theta equals 0 to just simplify things. And it mixes space indices, which is I, with gauge indices A. And so SU2 is sort of gauge is mixed in with SU2 rotations. Okay, and there's some constraints on these numerically determined functions, A and Q. Basically, there's 0 at the origin, symmetry is restored inside a monopole, and it's broken outside. So what people did then to get the Dyonic states is first, what Julia and Z did was they just let A0 be non-zero and just be like, fine, Topf-Polyakov found their solution with 0 electric charge. They found a solution and said, here, these Julia Z dyons could be, well, when they did it, they did it classically, and it could have actually every single electric charge. They got any minus infinity charge, plus infinity charge, anything. To get discrete charges, you actually had to quantize this theory. And so if you quantize A0, you then get discrete charges, 1, 2, 3, 4, 5, or -1, -2, -3. And people sometimes very sloppily call these dyons, or these sort of excitations, bound states of the W boson with the dyon, or with the monopole. If you really decide to try to take this interpretation, they can calculate the change in mass. It's of order alpha times mw. And so if you really wanted to interpret this as a bound state, it is a bound state of order mw binding energy. And so rather than having binding energy alpha mw, it's more like 1 minus alpha times mw. So this sort of led us to think, are there other bound states? And so what did we want to do? What we wanted to do was literally just solve the Dirac equation in the background of a monopole, a la how we solve the hydrogen atom, right? We just wanted to say, let's do this dumbest thing, Dirac equation, hydrogen atom, solve for all solutions. There are a few.
Just sorry, just to make sure I'm following. I mean, the monopole. I don't understand the bound state thing, because I mean the monopole has a huge mass, right? Like 1 over alpha mw, right? And this is alpha mw above that. So in what sense does it have binding energy of order mw? I don't know.
So this is saying if you interpreted, it's there.
Oh, because you're saying the continuum states are a monopole plus a W.
Yeah. They're saying
there's also a photon though.
Yeah, so the photons don't have charge. So these Dion states have charge 1. And because my theory here has the only charged particles are W bosons, people
that makes somewhat
sense. It's quite sloppy. I don't actually think it's an accurate assessment.
No, I just wanted to make sure there wasn't something simple I was missing. I got it.
Yeah. But this was only just sort of motivation to just look for all bound states. And so what I want to do is just add some fermions and then just like the hydrogen atom, just solve the Dirac equation, find all bound states. There are a few things you have to note. First is, like I said, with a monopole, you have to specify boundary conditions at the origin. These are UV dependent. And so if your bound states have any support near the origin, then you have to be careful about what boundary conditions you put there. The second thing is you need to take into account the anomaly. The Dirac equation, very famously, phase of the mass term doesn't matter. Phase of the mass term is critical for things like theta. And so you need to at least take into account some bit of extra quantum, not just quantum mechanics, but a little bit of loops and things like that to sort of somehow take into account the anomaly. Okay, so this is basically going to be my goal. So the basic outline is I'm going to first talk about the Witten effect with light fermions. In other words, this is the ground state with no with fermions, but it's the ground state with no bound states or anything like that. What is just the ground state of a monopole with fermions in the spectrum look like? So this is work basically done by Kellen. I'm sort of going to talk about it a bit to sort of introduce all the approach. Next, I'm going to sort of just do what I said, find all the bound states to the Dirac equation. And then at the end, hopefully I'll have time to sort of talk about some of the subtleties in the massless limit. Okay, so first, this is the theory I want to look at. Basically, 't Hooft-Polyakov monopole, add an adjoint, and then add two fermions and with a mass term. And I just want to say, what is the ground state of the monopole here? With a theta term and a mass for the two fermions. I'm going to label one of them as baryons, one of them as leptons. So in other words, at low energies, I'm just going to have two objects with electric charge. I'm going to call one of them the baryon, one of them the lepton. In this theory, they both have charge 1/2. And all I'm going to do is find the ground state. So like I said, I'm just going to solve the Dirac equation. Due to the Witten effect, things are going to have electric charge. So I also want to solve Maxwell's equation. The kinda of solving the Dirac equation is the fact that I also need to take into account the anomaly somehow, that one loop effect. And so the step to doing this is basically, I'm going to reduce to the S wave since it's likely the solution is spherically symmetric. So go to the spherically symmetric limit. I'm going to derive what the boundary conditions are. Since I specified my UV completion, I've specified my boundary condition. I'll turn it into a 2D problem. I'll bosonize it, which is basically the trick that takes the Dirac equation and will let you take into account the anomaly. And finally, I'm just going to numerically solve it since my analytics is not strong enough to solve these equations. Okay.
So just to be clear, you added two Weyl fermions or two Dirac fermions?
Two Dirac fermions. So I added one Dirac SU2 or two Dirac U1s. Yeah, so at the low energy point of view, after you integrate out all the SU2 physics, you'll have two Dirac guys. The one I'm just calling the baryon, the other I'm calling the lepton. From the SU2 point of view, I'm adding two Weyl fermions, so a single Dirac in the fundamental. Yeah. And for now, I'm doing the simplest case where their mass is exactly the same. Okay. So let's reduce to the S wave. So, all right. So what is the S wave? Well, you break SU2 gauge times SU2 rotations down to SU2 diagonal, which is basically what I drew here, where the diagonal guy J is both your orbital angular momentum, your spin, and your isospin combined. In the process, you discovered an annoying minus sign that basically we define gauge transformations for Lorentz symmetry and gauge transformations for internal symmetries with a relative minus sign, which is amusing if you've never noticed this, but it's unfortunately true we use different conventions here. And so since we want total spin, total J, 0, there are two ways of doing it. You can either have L equals 0, orbital angular momentum. You could have spin up and isospin down that cancel each other. So that's this G piece. And because there's no orbital angular momentum, depends only on R and T. Or you could have orbital angular momentum. So L equals 1, but spin 1/2, minus 1/2, and isospin minus 1/2 to cancel it and get 0. And this is what I'm calling this P field. And you'll notice it has an R hat dot sigma. So it has phi dependence. It has theta dependence. It is an annoying state. You can even work it out and show that it is the angular momentum, orbital angular momentum L1, and then sigma minus 1/2, isospin minus 1/2. So combined, these are both J equals 0 sort of angular momentum S-wave states.
So you don't have to use monopole spherical harmonics to do this, or
Excellent. Because if I tried to go beyond the S-wave, I would. But this is basically just the S-wave monopole spherical harmonics. It is, I sort of broke it down into two pieces that are easy to understand, but then the orbital piece is more complicated. And just for simplicity, I'm going to be ignoring those guys for now. So in particular, I made the assumption that the ground state is spherically symmetric, which seems like it's probably a reasonable assumption. And two, when I look for bound states, this means I'm neglecting all guys with orbital angular momentums non-zero. So I'm only going to have a subset of the total bound states. Yeah. Okay. So what is the boundary condition? Turns out it's quite easy to guess, right? Because what happens near the core of the monopole? Symmetry is restored. So in other words, this breaking of SU2 rotations times SU2 gauge unbreaks itself. And you can see if I have orbital angular momentum, you're going to be pushed really far violently away from the core of the monopole. And so if you had to guess, you'd be like, well, the boundary conditions at the origin are just P equals 0, right? Because it's the guy that even though it looks like when you combine isospin and rotations, you have S wave, at the core, you know the difference between isospin and rotations. And you're like, you have angular momentum, get out of here. This is very high energy. Don't. And so at least in the limit where you take the monopole size to 0, you would guess just if you have angular momentum, you're not seeing it. It's worth noting that this boundary condition, you notice, ignore P. You see it's diagonal and it mixes isospin and spin. So it's changing left-handed baryons with right-handed leptons and vice versa.
so somehow this disagrees with the Yan and Lamb boundary conditions.
So for them, I'm trying to remember what they did exactly. These are the charge violating boundary conditions. And so physical processes, it'll be some combination of finite energy and these boundary conditions that limit things. But I think these are the ones that people say are charge violating.
So charge gets deposited on the monopole
Yes.
from this boundary condition.
Or if you ignore all electromagnetic effects, this is the boundary condition that you say, yeah.
All right, I think that's what they said.
So then
that's good.
Then it actually agrees
You
with
agree
them.
with them. You agree
Yes.
with them.
Correct. And so actually, the fact that it's charge violating means that you have to be careful when doing numerics to enforce, like, well, either way, I'll get to it later. Okay, so you can also see all of this just analytically. You just gauge fix near the monopole, A0 equals 0. This is a nice chargeless gauge fixing. Just solve the Dirac equation. You see that P has bad 1 over R behavior, so you want to set it equal to 0 near the origin.
Sorry, so just for somebody who's not following monopoles, why is it okay that this violates charge, electric charge? I mean, that's supposed to be unbroken everywhere.
Great.
What do we mean? You say it violates charge conservation. Can you either say what that means or why
it means that this guy is depositing charge. It takes your monopole and turns it into a dion. So you can deposit charge as long as you excite the monopole.
You're saying that any solution with P equals 0, there's no solution that is static because there's somehow a rate of charge being deposited, or what?
This is saying, okay, so this is a little bit more in the future, but this is saying if you throw in a lepton, set alpha equal to 0, throw in an electron, it'll come out with charge. So throw in some charge 1/2 electron, it'll come out as a charge minus 1/2 baryon or lepton, depends on your boundary condition on your UV completion. but it comes out charge opposite charge, which means that you've deposited charge 1 onto the monopole.
Okay, I got it.
Which costs 0 energy when alpha is 0. And it costs a huge lot of energy when alpha is non-zero and the core size of the monopole is super, super small. And so actually, all the dynamics are actually fixed by both finite energy or minimizing energy plus these boundary conditions. Yeah, so in some sense, when people call them charge violating, they have in mind the process I just described, even though it's conservation of charge holds. Yeah. I guess it's more accurate to say it's deposition of charge in the monopole.
It's like when the signs say you got to conserve energy by turning off the lights, right? Energy is always conserved, but you know, yeah, I got it. You're not, I know what you mean.
Yeah. All right. So yeah, you can see this analytically as well, but I think it's the source of the P basically blowing up is the fact that you have angular momentum, real angular momentum in the problem. Okay, next I'd said, right, these guys R and P, G and P depend only on R and T, so which is a half plane. So it turns out you can just define 2D fermions involving your G's and P's, right? You take your pieces of your 4D fermion, which are spherically symmetric. You can combine them into 2D fermions here, which just you'll notice has a kinetic term, a gauge piece. So I could have just gotten rid of the second piece and write it a covariant derivative, and a mass term. And that's it. The bottom one is Maxwell's equations plus a theta term. So at this point, I'm going to have to do a trick that someone else sort of went through carefully, but we're going to bosonize the theory. And so there are 2 reasons to bosonize. One is, at least at my level of sophistication, programming Mathematica, basically, and Mathematica doesn't like Grassmann numbers. So if I wanted to solve the Dirac equation here, I'd have to deal with Grassmann numbers, namely these G's and P's are Grassmann guys. The other thing is that if I just take it straight at face value here, and I'm using the full Dirac equation, the phase of the mass term is unimportant, and so it misses the anomaly, which is critical to the Witten effect, right? Because the theta depends on, theta bar, the physical theta, is the theta you put into your theory and the phase of the mass term. And so if I really want to fully understand monopoles correctly, I need this one loop effect. And that's what actually bosonization will do for me. That's actually the only part about it that I care about. And so what is bosonization? It is a quantum duality between a 2D scalar and a 2D fermion. And like all dualities, so let's say duality of QCD and chiral symmetry, right? QCD confines, some very important non-perturbative stuff happens, but it turns into a lot of that when you dualize it becomes classical physics, right? You do classical physics of your chiral perturbation theory, for example, and you get a lot of non-perturbative physics out of it. For example, you see that the condensation of fermions and things like that. And so the fact that this is a quantum duality is great for me because it takes what was a one-loop quantum mechanics or quantum anomaly and turns it into classical physics or tree-level physics, which is great because that's what my computer does. It solves some tree-level equations. And so the only part of the quantum mechanics that I cared about, the anomaly, is now classical physics, which is great. I deal with bosons, which are great because I don't need Grassmann numbers. If you try to do anything more than just sort of, let's say I wanted to do quantum mechanics, quantum field theory out of this, you'd get a little annoyed. Why? Because I bosonized the radial and time directions of the field and not the angular phi and theta pieces, which I left in the fermion point of view. And so if I want to do like loop level calculations or anything, I'm shit out of luck. I'm not going to be able to do it. And so I'm good for me is that all I care about here is the classical level things and don't want to make sure I get quantum RG running correct or anything like that.
Question?
Yeah.
Would you agree that there is at some level an uncontrolled approximation here that's basically dimensional reduction?
Yeah. So there was a critical thing. I said, I went to S wave and I said, the ground state is probably spherically symmetric. That may not be true. And if it's not, I can't see that in this analysis because I threw away those modes.
Well, it's more, I mean, the way I think about it is that if you dimensionally reduce to a 2D problem, and then
Yeah.
you look at the quantum mechanics of that, you're only allowing the fluctuations to be 2D. And we know that
Yes.
those are very, very different, right? The counting of
Yep.
modes is totally different and so on. And so
Correct.
still, it might be fine if everything is completely IR dominated, et cetera. It might be okay, but it is an uncontrolled approximation as far as I can
Yes.
tell. Do you
I think
agree
I would
with all
agree
that?
with that.
Yeah,
Well, I mean, it depends a little bit. If you say like at a fixed radius r, you can be like, oh, I'm throwing away all modes that have energy above 1 over r, because those are the higher angular momentum modes will all have higher energy. But then I can't consistently apply that criteria with smaller radii as things get higher and
right,
higher energy and whatnot. And
right,
so there is an uncontrolled thing here where you just sort of have to hope it works. It's sort
right.
of like saying like in RS or any of these extra dimensional things where your UV cutoff is distance dependent.
So I mean, and that, yeah, exactly. So then can I press you just a little bit
Yep.
on the anomaly? Because the anomaly is certainly a dimensional dependent thing. And at least one way to think about it is that it is very much a UV thing, right? Because it depends
Yeah,
on.
that's right.
So, but you're claiming that nonetheless, this procedure is capturing the anomaly. Is there
Yeah.
more you can say about that? I mean, or just
I think the statement is in 2D,
convince
the
me?
anomaly exists as much as it does in 4D. Right.
Well,
If I
it's
take
very
2D,
different. I mean, it's a 2-point function in 2D. It's a 3-point function in 4D. It's not there in 3D. I don't know. It seems very dimension dependent. I agree it's there.
Mhm.
I'm just asking you to convince me that this is right. I mean, you told me perhaps there's there's an uncontrolled approximation, but then that seems to in what how why do people believe that this bosonization correctly captures the 4D anomaly?
Well, when you bosonize the theory, it is true that your final theory, the only physical theta is theta bar. And
Okay.
it is true that when you rephase your fermions and things like that, you get all the behavior expected from 4D anomalies. I think that's mainly the reason why people believe it captures everything.
Maybe you'll
Um,
point out some of the specific things that work. So theta bar, I understand, but you said other things also agree. Maybe you can point those out or.
what else agrees? So I think the statement is what people have also done is not bosonized, not done all of this bosonization, and solved the Dirac equation in the presence of a monopole. Then, if you ignore the fact that you're not sensitive to the phase of the mass, let's say, so what other people, I'm not going to defend this, but what other people have done is they just took the mass to be real and theta to be non-zero, and then solved the Dirac equation, filled up the Dirac sea, and observed the Witten effect. The solution you get doing that is going to be the same as if you bosonize and then set alpha equals 0.
Okay.
So because they were doing it assuming alpha equals 0, you have to compare assuming alpha equals 0, and you get the same solution.
Okay.
Now, this is just saying non-anomaly physics seems to match in the S wave. The anomaly physics I think the best I can say is it has all the 2D version has all the same feel as the 4D version. And so people think it has at least the important pieces of it.
Okay.
Yeah. But yes, I agree. You have to do a sort of, well, it's in some sense, it's the same thing you do when you solve the hydrogen atom, right? You just assume, throw out all angular modes and solve for the S wave state, bound
No,
state.
no. There it's fine. Okay.
Yeah.
Okay. There it's okay. Because the thing is you should keep all the S wave states, not just the ones where your individual fields are all in the S wave. You see what I mean? So I mean in
Yeah.
quantum mechanics, there's only one degree of freedom. And so there's
Yeah.
no approximation. But here you're assuming that every field is in the S wave. You're
Yes,
throwing
that's right.
away most of the S wave states by some counting, right?
Yeah. But I would say that sounds like it's a reasonable thing if all I'm doing is finding the ground state. It'll be more of an issue when I try to find bound states, or if I want to talk about multi-Fermi excitations and things like that.
Okay. Well, I'm just, yeah, I want to hear the rest of your story. I don't want to completely stop you. So
Yeah.
why don't you go ahead?
No, I'm happy to have questions. Okay, so how does bosonization work? If you just choose a gamma matrix, what happens is the spin up moves to the right and spin down moves to the left. This is just the solution to the Dirac equation. And so the way you bosonize is say, well, the right hand moving fermion is equal to an exponential of a right moving scalar. A left moving fermion, which is spin down, is equal to a left moving, or e to the exponential of a left moving scalar. Now the scalar itself has both left moving and right moving pieces. And so to isolate the left moving or isolate the right moving, you have to do this phi plus or minus an integral of a derivative, which is what you see down here. But if you actually put in left moving and right moving, you'll see this is exactly the combination of field minus integral of derivatives that uniquely selects left moving or right moving. Okay, but this is basically the essence of it, is just, this is why Mandelstam, Coleman, and them sort of guessed this originally. It works just as well in 2D, but you need to add mirror fermions to get on the other side of R equals 0. Okay, so you go through this, you go through annoying sort of boson is the sort of normal ordering, and what you find is the Dirac equation plus Maxwell E&M turns into this guy here. So there's your kinetic term to the left, there's a mass term, a sine-Gordon mass term in the middle, and there's alpha E&M corrections over on the right. Right, that's basically E squared as a function of radius. And the original boundary condition turns to phi b equals phi l. So in other words, yeah, so it turns out the derivatives being equal to negative themselves are unimportant. When you numerically solve it, you actually get something stronger, which is the derivative is always equal to 0. Finite energy ends up giving you stronger things. Phi b equals phi l will actually basically be imposing that u1b minus l is a nice quantum sort of integer object because it's an unbroken symmetry, should be an integer. That's what phi b equals phi l forces.
Can
Okay.
I ask?
Yeah.
Oh, sorry. I didn't. I just want to know what all the ingredients are. It just disappeared. What is theta m?
Phase of the mass term.
Oh, I see. Got it. Okay.
And theta is the theta term.
I got it.
And so you'll notice you can shift your scalars, which you'll notice fermions are e to the I times phi. So shifting a scalar is like rephasing your fermion. And you can shift that into the theta term. And you can see the only physical thing is theta minus the phase of the mass term. So I can move into the basis where all of theta is in the electromagnetic piece. Yeah. All right. So at this point, you just solve the ground state numerically. It's right. It's a sine-Gordon equation, classical physics. Solve it. You have to be careful because you need, when you solve this using putting a bunch of lattices, you need to make sure the lattice gets really close to the origin so that you can see that this alpha over r squared piece becomes important near the origin. So you have to take small enough lattice points that it becomes important. But either way, you get charge localized around the inverse mass, which is perhaps not too surprising. If you plot it in terms of your scalar, what you basically see is three different pieces. It's locked by gradient and the electromagnetic piece near the origin. So basically, it's really hard to deposit electric charge near the origin, so you don't do it. Everything is a constant. The mass term becomes important. And as always with mass terms, you start falling exponentially. Actually, though, the asymptote is a polynomial fall off for everything. Asymptotically far away from the monopole, you don't have exponential fall off. You only have polynomial fall off. In particular, you can calculate the charge far away. It falls off as 1 over r to the 5th, which is with no exponential. And this is basically required because of the anomaly equation, because far away from the monopole, alpha ff tilde is E dot B. E is falling off as 1 over r squared. B is falling off as 1 over r squared. So you can't have an exponential fall off very far away from the monopole because you have this 1 over r to the 4th term in your anomaly equation. And so this is basically why far away from the monopole, things are not falling exponentially. They're only falling polynomially. It's just, in some sense, it's a double check to show that you have, you still satisfy the anomaly equation and things are working.
The thing that you're talking about not falling exponentially, I can think of it as some sense as the fermion wave function.
Yeah.
In the ground state, in
Yep.
some sense. Some bosonized sense.
Here I'm just saying this is the charge density. Talk about something physical. Don't talk about fermion wave functions or anything. Just calculate physical thing, charge, density. Yeah. Okay. Great. I'm running behind schedule, but oh well. So let's talk about the massless limit really quick. So the Witten effect is saying the charge is always theta over 2 pi, regardless of what happens. In the massless limit, theta is unphysical because I can rotate it away. And so what gives? So a lot of people thought about this carefully. And the answer is basically an observer. So it's an order of limits issue, which is when you, if you imagine yourself sitting, so take finite mass, imagine sitting very far away from the monopole. You'd say, okay, this charged fermion vacuum is within your radius. And so you measure the total charge as g theta over 2 pi. Eventually, as you slowly dial down the mass, this charge expands away farther and farther and eventually passes over the observer. And now the observer would say the charge is 0. And so if you want to ask, how did Witten get that the electric charge is always theta over 2 pi, but in the massless limit, I can use the anomaly and rotate it away theta? The resolution is just that an order of limits, the distance of the observer versus 1 over mass. In addition to this, you'll notice you change your definition of the monopole in the whole process. When theta is, when the observer is very far away, you call the entire thing the monopole. The core of the monopole plus the charged fermion vacuum surrounding it. You say all of that is the monopole. When the charge expands past it, you say, the only part of the monopole is the core of the monopole. And so you also change your definition of the monopole in these two limits. So it's a combination of two things, order of limits issue, as well as your definition of the monopole. Whether or not you include this sort of fuzzy 1 over m distance stuff. Okay. Almost all of my time spent on the intro. Okay, let's look at the bound states. So what I'm going to do now is look at a scalar adjoint. So, the Topf-Polyakov monopoles, and this time I'm just going to throw in NF fermions. Turns out there are two different types of mass terms. I'm going to ignore one. For now, we can ignore the Majorana-like SO mass terms and just write Dirac mass terms here. Turns out this breaks your SU and F symmetry to SP and F. So I'm just going to call this mass term SP, preserving. if you want the difference between these two is basically, do I put both parts of the baryon? Well, you can just imagine, does a UVW boson take a baryon into an antibaryon, or does it take a baryon into a antilepton? And I'm going to be doing the case where it takes a baryon into an antilepton. So B minus L is preserved, but B is not, L is not. So I'm only going to be looking at the guy on the right. So might as well just say bosonized theory is the exact same as before. So going very slow, but let's very quickly just do an NF equals 1 case. Of course, due to the anomaly, right, the Witten anomaly, you have to have even number of fermions in an SU2 case, but you could imagine giving one of them a heavier mass and integrating it out first. So this just says find solutions to this sine-Gordon equation where there's just a single mass scalar with a single mass term in the electromagnetic piece. You can say finite energy forces, there's the electromagnetic piece, which forces phi equals theta at the origin, because 1 over r squared says huge amount of energy is phi not equal to theta at the origin. And then away from the origin, the mass term says sine phi has to be equal to, or rather cosine has to be equal to 1. So at infinity, it has to go to 2 pi times some integer. So every solution I'm going to look at will just be characterized by some integer q. So it turns out this q is actually, I'm really finding Dyon states, because you can say q equals 1 is equivalently to saying that solving the same set of equations with theta equals 2 pi. Q equals 2 is equivalent to solving the theory with theta equals 4 pi, etc. So at least for this simple example, looking for bound states is the same as finding the Dyon solutions, which there's one thing to note. There is always a solution for a Dyon, which is a monopole at the center and a fermion at infinity. This is always a solution. And in fact, often it is the minimum energy solution. So the lowest energy state is very often a Dyon sitting, a monopole sitting by itself and a fermion off at infinity. Turns out that you can actually analytically show this if the charge is greater than 1, that this is always the minimum energy configuration. If the charge is less than 1, well, then you have to think a little more carefully. In a small alpha limit, you can sort of analytically do a lot of things, but don't really have time to go over that. So here's an example of a solution. D0 is the monopole. So I guess since it has charge minus 0.2, I'm setting theta over 2 pi equals minus 0.2. And then D1 is the Dyon state with charge 1 more than it. And it has an electric charge 0.8. In both cases, the charge as a function of radius is basically all determined around m is 1 over r, or r equals 1 over m. And so if you analytically solve it, this is what happens. I chose alpha equals 0.6. And the numerical solution is in blue here. And what you'll notice is eventually the classical solution for the monopole ceases to exist at a particular theta, because you're cranking up theta so large that it's turning into a Dyon, and it wants to re-emit a fermion to turn back into the smaller electric charge, smaller charge guy, which is basically what was the Dyon and is becoming the monopole. And so at some point, it ceases to exist. An amusing thing is if you actually interpret the monopole or the Dyon as either the Dyon or the monopole plus a fermion and calculate its binding energy, the binding energy is slowly increasing as you cross theta equals pi. And actually, before the solution classically ceases to exist, the binding energy is greater than 1, meaning that the monopole, or what used to be the monopole and now has very large charge, has energy more than what was the Dyon and is now closer to the monopole plus a fermion. So in other words, this guy at some point becomes quantum mechanically unstable to decay. It's classically stable, quantum mechanically unstable to decay, sort of like any nuclear physics nuclei, where you have to do a tunneling calculation to get the decay rate. And eventually, as you crank up theta, it becomes classically unstable and just emits classically. So for fun, you can do things like solve this as a function of alpha. And as alpha increases, this theta, sort of this critical theta at which it becomes unstable, starts decreasing. Okay, so that's all I have to say about a single fermion. Now let's talk about the two fermion case. And if the masses are equal, you get a full sp2 symmetry. If they're unequal, you get just a u1b minus L symmetry. Okay, so again, go through, solve all the Bion states. Minimum energy solution is saying theta equals phi. Remember, theta b equals theta L at the origin. This is what forces quantization of b minus L charge. And so finite energy at the origin forces both of them equal to theta. And now either of those can go to an integer at infinity. And so all solutions are labeled by these two, NB and NL, which if you do a little bit of math, are basically the electric charge, Q, or Q over 2 minus theta over 2 pi, and its B minus L charge. So now you actually have genuine bound states, right? Things that have B minus L charge, so they're not dyons of any sort. And so there you just get a whole plethora of states. Turns out you go through the same stability analysis before. What you'll find basically is there only ever, at any given point, 4 guys that could even potentially be classically stable. The would-be monopole, the would-be dyon, and then the 2 monopole plus a baryon or a lepton bound states. So you can just solve it. You get here's a solution. Again, everything is deposited at charge m r equals 1 over m. If you start making the masses very differently, conservation of B minus L charge, in other words, B minus L being 0, means you deposit half the charge, half the Witten effect is due to your baryons, half the effect is due to your leptons. And so you'll notice the total charge at long distances is the same for both of them. The baryon is deposited at 1 over R baryon. The lepton is deposited at distance 1 over R lepton, or 1 over M lepton. And in between, there's a little bit, you'll see, I had to crank up alpha quite large to see an effect here, but there's a little bit of a bump where the lepton tries to deposit negative charge, or in this case, positive charge, to screen electromagnetic effects. And so there's a small amount of electromagnetic screening, turns out to be extremely inefficient. So from the real world point of view, there's effectively no screening. And only comment here is that theta dependence in here, a lot of it is driven by the heavy particle, not the lighter particle. Basically, because B minus L forces you to have deposit charge both at 1 over M baryon and 1 over M lepton. Okay.
Why isn't there an energy difference?
Yes. So, where is this? Excellent. Actually, I don't have exactly that plot, but I have following. Here, this is the energy difference between the monopole at theta equals 0 as you vary theta. And in particular, as I vary theta by order 1, the energy of the state changes by order of the baryon number, or 100 times the lepton number in this case. It'll actually, I won't be able to get to it, but a fun fact is this is quite reminiscent of how SU5 works. In SU5, the lightest particle is the electron, but it's not actually what determines theta dependence. It's actually the heavier proton, or yeah. Okay.
I'm just wondering if I'm depositing electric charge in this cloud, if I make the cloud bigger, there'll be less self-energy in the cloud.
Yes. And what forces you to have it at 1 over m is this mass term in the top right corner.
Right, but when you have 2 different masses,
yes,
it seems like it'd be more efficient energy-wise to put all the charge in the lightest mass where it's more spread out.
And in fact, the only reason it doesn't do it in this case is because you have a B minus L symmetry. So you want to put in a fractional charge, let's say 0.5 charge. If B minus L is 0, I have to put 0.5 electric charge in baryons, 0.5 electric charge in leptons. I'm unable to put it all in leptons because of a quantized U1B minus L. There's a different mass term, the SO mass term, that I don't have time to go through. That theory is exactly the same as this with no B minus L charge. And in that case, what you say is exactly true. It just stops throwing charge into the baryons and throws it into the lepton instead, the lighter guy.
Thanks.
Yep. Okay. Great. So some solutions. Okay, here's actually something that surprised me at least, which is you can just ask, what is the lowest energy state in the problem? Like that has magnetic charge 1, as a function of theta. And it turns out for theta near pi, a monopole plus a fermion has less energy than a monopole itself. In other words, by adding a fermion, this combination state has less energy than the monopole, which is, I find, quite amusing. Here is basically the ground state as a function of the mass ratio, B minus L. And this is what the solution looks like of a charge 1, B minus L equals -1 state. So B minus L equals -1. It tries to put all the energy in the lepton if it can. The baryon is only 10 times the mass, so it still puts a little bit in the baryon. You'll notice it puts a small amount here, 0.2 of it, and 8.8 of it goes into the lepton. Okay, so turns out this effect here of the monopole plus an electron or proton being lower energy than the monopole state by itself is entirely due to electromagnetic effects. And so it's only important near theta equals to pi. I'm really out of time, so I won't go into the details, but you can actually show that this is all electromagnetic. And so you can show, for example, the number of stable states at any given point. And so at the very bottom is theta equals 0, where the only stable state is the monopole. But you can see above theta is a few, just a little bit, you actually have 3 different stable states, or rather, actually 4 different stable states. You have the monopole, the dion, and a monopole plus with charge B plus L, B minus L plus 1 or -1. And so actually, the stability diagram is quite amusing. There's a lot of stable states as soon as you get away from theta equals 0 here. Okay, so how fast should I speed through? Because I basically used up my hour, and I don't know if I should speed through.
How much time do you need?
Probably another 15 minutes is what I had planned, but.
So why don't we do my suggestion? I don't know. So my suggestion is, why don't we go for another 15 minutes so you can tell the rest of your story, and then we will clap and people are okay to leave and people who want to stay, if you can stay a little longer.
Okay.
Does that sound okay to everybody, or is that okay? Okay.
All right, great. All right, so, well, larger mass splitting is destabilize the monopole and dion, but we can go that. Okay, so I wanted to talk briefly about SPNF greater than 4, greater than or equal to 4. Turns out you get a whole plethora of stuff. You get like 4 different types of fermions you can bind. You can go to 3 fermion excited states, 4 fermions, etc. There are actually quite a number of states. Turns out for the equal mass case, you can actually study things quite well. So let's just ask, what is the number of stable states around theta equals 0 when all the masses are equal? For bonus, you can actually even also calculate when the monopole becomes unstable to decay, how large theta has to be. So turns out, because you have 4 fermions with equal mass, you might as well just look for a solution where every single fermion is doing the exact same thing, or every scalar is doing the exact same thing in this case. So you can basically, since I already solved just now numerically NF equals 2, I can just say SP4 is just 2 sets of the 2 scalar case. Really, I could just say it's 4 sets of a 1 scalar case if I wanted as well. And you'll notice, if you look at this for a moment, so what happens is I get NF copies of the scalar, but in the electromagnetic term, because all the scalars are the same, they go effectively from charge 1/2 to NF over 2. So if I want to look for an equivalent, I can basically, what happens? Once I set all the scalars equal to each other, it's equal to the one scalar case with just a few rescaled parameters. Namely, alpha is slightly larger, NF times larger, and the effective theta angle decreases by 1 over NF. Right, so this is basically, all I did was take the NF equals 4 guy and then set up all the scalars equal to each other. And that 2 in front of the effective theta is basically just the statement that fermions happen to have charge 1/2 as opposed to 1. Okay. So what happens? This is just saying, well, it's a bunch of scalars with theta slightly smaller. And this looks like just a bunch of copies of the Witten effect, right? So what is the bound state of the dyon? The bound state of the dyon is theta equals 2 pi. And so that looks like the effective theta is 4 pi over NF. And so if NF is larger than 2, this looks like it's just, oh, it's like a single scalar case or single fermion case with theta equals pi. 8 would be like pi over 2, etc. And so you can just import over all of everything you did for the NF equals 2 case. And you can find some exact solution. For example, when theta becomes unstable, the number of bound states, etc. These are just for the different theories. You can solve for the number of bound states, and you can get some analytic formula that basically they're of order NF of them in the large NF limit. So in other words, this is saying if I take theta equals 0 and a bunch of equal mass fermions, I have a whole bunch of stable states that do not want to emit fermions to infinity, right? Because like the first dyon state is like exciting the W boson. So in principle, an equivalent solution is putting 2 fermions off at infinity and monopole by itself. And the claim is just, well, that solution has a lot less energy than just bringing them in and then having fractional pieces of the sort of theta vacua excited. And you need NF of these stable states, which are sort of single 0 fermion, 2 fermion, 4 fermion, 6 fermion, 8 fermions. They're basically like the dyons excitations are a bunch of stable fermion states. So, okay. Whew. Okay, so let's talk about the massless limit, because this is something people care about and have thought about a lot recently. So what happens when you have, I sort of described the Kalin-Rublikov effect for NF equals 2. Let's talk about NF greater than 2, so 4 or larger. So if you take the theory, like I wrote here, it has an SUNF flavor symmetry, and you throw in one of the fermions, let's say the top piece, psi, and you look at what are the final states, S-wave final states that preserve all symmetries, and you discover there is no S-wave final state that does this. And so people are sort of, when Kalin did this, first, he got very confused, did crazy things like postulating non-conservation of electric charge and things like that, which obviously we all know nowadays can't be the case. So one of the things people have done was notice that, well, this looks like you have a chi particle plus some charge 2 state. People sometimes call this charge 2 state as some like 2 over NF sum of all the fermions. Either way, for me, it's just you have a charge 2 state in the S wave with no flavor symmetries. So this is what's sometimes called the semiton state. It seems to be to make to even have a final state in the S wave. People have said, well, you need a charge plus or minus 2 object with no flavor symmetries. I just quantized my theory. I know all the states of my theory. I know all the fermions. I know all the fermions reduced to the S wave state. How could I get this new final state into the story, right? You shouldn't new states shouldn't appear out of nowhere. And so this was a confusion. People have a lot of sort of differing ideas about this. I guess you can ask John for details. But the way I'm going to try to approach this problem is do the same thing as the Witten effect. We're going to take massive fermions and then slowly take their mass to zero and study the massless limit and see does anything subtle happen. So in particular, I'm going to take theta equals 0 at a Dirac mass term for everyone. This is the case I was just studying with an SPNF flavor symmetry, and then take the mass slowly to 0. And in particular, I'm going to be interested about the bound state, the Dion bound state, plus or minus 2, with no flavor symmetry. So in other words, this is the solution of the theta equals 2 pi solution, right? This is the Dion, first chart Dion. And so the easy way to solve this is just to set theta equals 2 pi plus or minus 2 pi and say that there are no baryon or lepton number and solve for a solution. And as I sort of mentioned before, this is just NF Witten effects of theta with plus or minus 4 pi over NF. Okay, and that's an example of the solution here. And so this is a bound state. It's the Dion of the theory. It has charge 2. It has no flavor symmetries, but it does have magnetic charge, right? So this is an object you'd call the Dion. Charge 2, no flavor, magnetic charge 1. If you interpret it as a sort of a bound state of fermions, you can analytically calculate its mass or binding energy in the small alpha limit. And you'll find that it's much, much smaller than the mass of any fermion. So it's down by NF. So as they take very large NF, this is basically almost the zero mode even. It is very large binding energy. And as you can see, the radii is of order 1 over m. Okay, so let's go back to the Witten effect briefly. So Witten effect in the massless limit. An observer sits at a finite radius. As you take m smaller and smaller, the radii of the polarized fermion vacuum goes further and further out until this charge sweeps over the observer. And the observer now says that there's no electric charge. And at the same time, you redefine your monopole from having an object of size 1 over mw to an object of, 1 over m fermion to an object of 1 over mw. You say it's just the core. So what case here happens here? So you sit at a finite radius, and the asymptotic states, or at least the asymptotic S-wave states, are your quantized fermions. Some fermions are ingoing, some fermions are outgoing, but you just have your standard quantized states. You slowly decrease the fermion mass until this bound state starts to hit your observer. And at this point, what does the observer do? They say, oh, I have a charge 2 state, or a charge 1 state, sorry. And since I redefined the monopole to be just the core, then what does this dion turn into? It turns into a monopole core plus everything else. And everything else is a charge 2 state with no flavor symmetry. So this new state, you basically say, because I'm sitting, what was a bound state has become so large of a radius that it's turning into an asymptotic state. Now, I won't claim to have completely solved the problem because there's some caveats here. I would say this shows that semitons exist as a possible state, asymptotic state. It doesn't say that my cross sections are non-zero. It doesn't say that maybe in the massless limit, I can't produce them and things like that. But at least to me, this seems to suggest that there's some physical origin to where they come from. Whether or not they actually solve the problem, you actually have to go do a cross-section calculation. And because of a lot of the things Marcus had said before, I'm very sort of a little uncomfortable trying to actually use all these things for dynamics rather than just solving for some nice spherically symmetric solution. Okay, so I'm way over time, but to conclude, I think monopoles are quite fun. What I was talking about here was just finding the S-wave bound states of a monopole. there are quite a few of them. Sometimes they're one fermion, sometimes they're two fermions, and whatnot. They tend, surprising to me, they have binding energy of order the mass. And so the radii of order 1 over the mass. In particular, their binding energy is not down by alpha or anything like that. It's just you have binding energy like 50% of the mass or like 90% of the mass and things like that. All right. Hope you guys had some fun.
Right. I think, as we said, this has gone a bit over, so anyone who would like to leave, but maybe we can have questions by people who haven't already asked questions, if there are any.
So right in the beginning, when you talk of Kellen-Rabakov effect, you're using a fermion you're using a spin half as example, so you can flip the chirality to make angular momentum conserved. So what should you do if you throw a scalar electric particle at a monopole?
Excellent. So what happens for a scalar, let's pull back all the way here. Where is it? Here. So you'll notice here, what's important to get an angular momentum equals 0 state is that you have spin 1/2, right? To get an S wave state that actually falls in, you need spin 1/2. And so what happens if you throw in a scalar? Well, you have L equals 1/2 plus 0. You come out, L is also a half. And so, or in particular, in this picture, it comes out pointing the other direction. And so, but you'll notice there's no problem there. This is when I really should have not drawn this classical picture and drawn more E and M. Okay, so, okay, here's when I regret not drawing this in the more proper S wave state. So what is an S wave state? It's falling in to the monopole, and eventually it comes out like this. And you'll notice at any given point, the only difference between the two is the direction of the momentum, inwards or outwards. So for a fermion, there is spin. If it's right-handed, that's saying its spin is proportional the same direction as the momentum. So when the momentum changes sign, going radially inwards to radially outwards, it changes by a half. Now, for a scalar, there is no angular momentum inwards or outwards from the spin. There's just the sort of L E and M equals 1/2. And so I drew this classically, but because I'm actually doing S wave states, I probably really should have done it quantum mechanically. And so I think that's really the source of the confusion, is that for scalars, what you'll find is that the short way to say it is for scalars, it has L equals 1/2, and L equals 1/2 doesn't hit the origin, right? There's an angular momentum barrier for anything that's not S wave. And so boundary conditions at the origin are unimportant for anything which is not an S wave state. Yeah, I could have drawn a better picture. Sorry about that.
Wait, so you are saying this only matters when the electron is close to the monopole, or?
It's when you have an S wave state, turns out to be. That's sort of the short way to answer it. The long way to answer it is just to say, do the same thing for a scalar. And what you'll find is that it's okay for a scalar to come out with unchanged. You'll still conserve angular momentum. Okay. So if you take this and throw out the spin 1/2 piece, you have angular L E and M 1/2. And when it comes out, it'll also have 1/2.
In the opposite direction, unless you...
Yeah, so this is why I said I should have drawn it in quantum mechanics using a spherical shell coming inwards, because an S wave state is not, it approaches from the left, hits and these out to the right.
So you're saying...
So you could take an initial state that's just a plane wave.
Yes.
And then it comes in from one side and then it has to backscatter, no?
Yeah. And so if you take a plane wave incoming, this is not fixed L. And so you're going to have to be a little more careful about the conservation of angular momentum.
I mean,
Okay.
I have to say, I also find this pretty confusing. Like,
Yeah,
I know that I can have helicity, just ordinary helicity amplitudes, like in QED, okay?
yeah,
And they can vanish in the forward limit, okay? And
yes.
I don't freak out about that, okay? I don't say they're missing an S wave or anything like that. You know, I mean, the real thing that's going on with the scalar case is that, you know, to write something down, you need to go to higher partial waves. You can, you know, right? I mean, then you can write initial and final states, but you're not only in the S wave, but you're making the S wave out of S wave modes. You're looking at S waves that are made out of spherically symmetric modes. Whereas, of course, what you can actually do is you can add non-zero angular momentum and get zero, right?
Yeah, that's right.
So somehow, I gotta say, I mean, I don't, as a total outsider who hasn't thought about this, okay, so it's very superficial. It just looks weird that there's this immediate spherical reduction, and it's not totally obvious to me that there's a problem if you go, if you were to not do that.
Yeah, which is why at the end I said there are caveats to any of this. Like I wouldn't have said I've solved anything. I wouldn't even necessarily said that there's a problem initially and things like that. Like
Like
my focus is
I
more
would be
on
really happy if somebody could convince me that there's a paradox, something mysterious, without ever, you know, talking about projecting onto the S wave. If there's
Mhm.
if there's such a qualitative paradox, do I really have to look at the S wave? I can't just, there's
So
no other way to say this paradox other than it's only for the S wave, it's very special, only for fermions, only for the S wave. I don't know. It sounds a little weird.
Yeah,
well,
I think
you can talk about helicity amplitudes. You have a massless fermion. It scatters and it comes out with the opposite helicity.
Right? What happens in QE? That happens in QED too, by the way, right?
No,
Yes, it does. Yes, it does.
massless electron changes helicity. Helicity is conserved. And
No, helicity is not conserved. Helicity is a Lorentz invariant quantum number. What's conserved is the total angular momentum. I just had my students calculating helicity amplitudes in QED, and some of them, the helicity of the particles changes.
there's only one particle, so it
So
can't.
nothing can happen to the monopole either. That's a new rule. Monopole can't
We're
do
talking
anything.
about a static background monopole. One fermion comes in on
Okay.
it,
Okay,
one comes
I'm
out.
an idiot. I don't know anything. It's just I would love to see this without, you know, just a full explanation without all this S wave stuff.
Well, I didn't say S wave once.
Okay, well, you can
Instead,
explain it to me
one
later. We
particle
don't have
state.
to, we
The
don't have,
helicity.
everybody else doesn't have to listen to you explain this to me, because I see you every day. So let's make use of Anson here.
yeah. I think the reduction for me makes a little more sense if all I care about is looking for bound states. Then I would say I'm looking at some ground state wave function that's spherically symmetric.
But can I
And
ask, would you say that this is, so bosonization makes your life easier, but do you think this is completely equivalent to just quantizing the fermions in the background, and maybe you gotta use a basis where the fermion mass is real, and if you just did that, everything would just work?
okay,
You get
so
the same answer?
yes.
What do you think?
So if you required if you impose fermion masses are real, then this is completely equivalent to just solving the Dirac equation by hand with some theta, with one additional thing, which is you have to by hand allow yourself to shift parts of theta between different fermions. So if the fermions have different masses, it's not like they're both gonna be balanced exactly the same, right? Like, what's a way to say this? There's in the real theory, there's only one free parameter, which is theta bar. When you solve just the Dirac equation, there is theta, and how you pretended the phase, how you treat the phases and the different mass terms of the fermions. So if you by hand set the phases of the mass term plus theta are equal to each other, and then just explored all the different solutions while imposing that the sum is all theta bar, then you would get the same solution. I don't know if I said that coherently or not.
Yeah, so you're basically, I think the answer is yes. You're saying that this is just a shortcut. But I thought that the problem was that in the Dirac case, you don't see that's what's supposed to be the case. What's supposed to be the case is you can move theta around and you get the same thing, but you couldn't see. I thought the problem was in the straight Dirac equation things, you don't
couldn't
see
see
that. So you just,
so
but I'm just
that's why
saying,
I'm
so but if you
saying
just as a prescription, put it all in front of FF dual, then I thought you said that should be the same as bosonization. So I'm just asking, is that the same when you now add more fermions, more masses?
it is only equivalent for when there's a single fermion. When there are two fermions,
You have to make
then
some other weird choice.
yeah, because you don't know how much of the Witten effect is distributed between the different fermions. That's something you have to put in by hand.
So it's not known like how to start from the monopole solution and find the effective Dirac equation or something by integrating out the core of the monopole. Seems
I mean,
like this ought to be, it's all weakly
you
coupled.
can find the effective Dirac equation. It's just it doesn't have one loop effects in there, right? You're doing classical physics. You say
So
here's
you
the
match
Dirac
it one
equation.
loop. So you match it
Yeah,
one loop. The
yeah. So
technology
then you have to
exists.
say do one loop matching, but then that's still saying at low energies you can always do a rephasing. You can still do a rephasing between the mass term and the theta bar, right? Because I'm not integrating out the fermions or anything like that.
Sure.
It's
You're
the
just
IR
integrating out the
symmetry that's the
monopole
problem.
core. Yeah, but we know something's missing and we know it's at one loop.
Yep.
So why doesn't somebody calculate that?
I mean, I think so. If you ask what equation is bosonization really solving, it ends up basically just solving where did I put it? The anomaly equation here. If you actually ask what is the equation of motion of the scalars, it is literally this anomaly equation. And so I think
I mean,
if you
to
took,
me, it sounds like you're saying, gee, look, all these wonderful things work. But I'm just wondering, since this problem has been talked about for over 40 years, maybe one needs an actual derivation from first principles, right?
Mhm. So I guess what you're wondering is how to properly take into account the non-radial modes.
I mean, it
Right.
seems like this is a long distance effective field theory. The short distance is the size of the monopole core.
Yes,
You want to approximate it as a point. So this
correct.
is I mean, it's not completely conventional. So yeah, you have to, it's not just integrating out a heavy particle, it's something else, but matching should apply. You should have some long
Sure.
distance effective theory and you should be able to identify what is the extra effect from,
Sorry,
one.
but if I don't integrate any out fermions, I don't change theta, right? If I have a monopole
Integrating
at
out,
15
yeah,
GeV and I integrate down to 100, integrate down to like 10 to the 5 TeV or 10 to the 4 TeV, it doesn't matter because I'm not integrating out fermions.
right. But the fermion propagator has a piece that knows about the monopole core if you're very close to the monopole, right? Because
Yeah.
in the inside the monopole, there's a weird electromagnetic field, and the
Yes.
fermions are propagating through that. And that is a short distance effect because the monopole is small. So it's a short
And
distance effect on a light particle that you're
yes,
integrating out.
which is theta independent, right? Because a short distance effect doesn't see the long range mass term, right?
You're saying that this will never give the right answer, or what are you telling me?
No,
You're
I'm
telling
just
me
saying
there's no way
what
to
you're trying
integrate
to
out.
do will never give the right answer,
It'll
right?
never give the right answer. Integrating out the monopole core will give you the wrong answer. So you have to use a model that puts in
No,
the.
I'm saying it gives the right answer. It just means to
Okay.
get the right answer, you need to see one loop anomaly effects. And the anomaly is not dominated at some UV scale. It depends on mass terms, right?
Well, I mean, as you said, there will be subtleties in taking the massless limit. I'm not just going to start with massless fermions,
Yeah.
probably, right? I'm going to start with, small mass fermions, but there are definitely short distance effects due to the monopole core. And
Yes. And I
that's
would
what's
say
causing everything. And so,
and if I'm integrated out physics to radii larger than 1 over m, then then matching will take into account everything. But if I integrate out to distances smaller than 1 over m, then I'm not integrating out all the fermion, only the UV contribution.
right.
Yeah. And my claim is that is theta independent. That does not change theta or anything like that.
Well, I mean, the theta term is still there, so it's not that theta is gone.
Yeah, but I'm just saying that EFT.
I mean, you said in your introduction, right? Somehow it's the effect of the monopole core. Somehow that's what's causing all of this.
Mm-hmm.
So if I integrate it out, I should get something that combined with all the light stuff that's left gives me these effects.
Yes.
Or some effects.
Correct.
Okay. Anyway, it's fine.
Yeah.
Nobody wants to do this. Okay. I thought we just had a talk by Takamichi Yukui, and I thought that Polchinski in some sense claimed to have done this, right? That there's some kind of, if you do this, if you integrate out the monopole core, there's one thing that's left, which is this rotor degree of freedom, which is localized.
That's right.
In some sense, it's not right to say that it's localized at the monopole core, but it's right to say that it's somehow associated with excitations of the monopole core.
Yes. I think I would agree with those statements.
Yeah. And so he's yeah.
And those excitations are super heavy, so you can integrate them out.
Okay. And so then you get, can you make you can't write a modified Dirac equation that gives you that allows you to move theta around, or you can or you can't? It should be able to.
I mean, the Dirac equation, as normally stated, theta is completely unphysical.
Yeah, I understand that. That's why something's missing, right?
Yeah.
Yeah.
And one should be able to discover it by actually carefully integrating out the monopole core.
Sorry, but the phase of the mass term is an IR effect. Why does integrating out UV physics teach me about the phase of your electron mass?
Because I think that if the monopole weren't there, we wouldn't have all these effects.
Yes, I would agree.
So,
but you don't need to say, the question is, how does the fermion vacuum respond to some source? The statement is the fermion responds to the source in such a way that theta, it acquires an electric charge theta over 2 pi.
Well, anyway, I should just shut up because I don't know how to do this. So I just, maybe, okay, maybe I'm just being stupid.
But if you want an answer to the other question of why haven't other people done this, well, actually, Bosenization and everything here was done by Callan. That was when he was trying to first solve these things and whatnot. This is actually the approach he used. But two, you'll notice a few years after this, one of the string revolutions happened, and everyone who was working on this went off to do the cool new thing. And so basically, if you're asking why did people ages ago not study this more carefully, it's because of that.
Yeah, sorry, we have to leave because there's another seminar now. Okay, so I'm sorry, we have an IR cutoff. Okay, so yeah. Listen, thanks. That was cool. I'm sorry it took up so much airspace here.
Sorry, I had to speed along at the end.
Okay, let's clap again. Thanks, Anson.